Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk on continuity of a state. What does it mean, continuity of a state? A careful examination of isotherm plotted in figure 2.11. I am going to show you. This is the figure 2.11. You can see this is a graph of pressure volume isotherm of carbon dioxide. So look at here A, here B, here C, then look at here G, here F, here D, here H, and here E. Just remember here from C, G, X, F, D, and these positions. So these figures shows that it is possible to convert liquid carbon dioxide into gas and vice versa without any discontinuity, that is, without having at any time more than one phase present. On joining the end of horizontal portion of various isotherm, a bonding curve CGXFB represented by dotted line is obtained. At the top lies the critical point X with in the area of boundary curve. Both liquid and gaseous state can coexist, but outside the area, either liquid or gaseous state alone can exist. Because of this coexistence curve, it is possible to distinguish between the two states of matter, namely gas and liquid. However, in practice, this is not always true because it is possible to convert matter from one state into another without any sharp discontinuity. So this can be done as shown in figure 2.11. Increase the temperature of gas keeping volume constant. The pressure raises along xy, and having reached y, the pressure is kept constant. The ideal gas is cooled, and this decreases the volume along the line y. So we have passed from x to z without the gradual change as it occurs along the line BC. That is, condensations in the usual sense of term did not occur. Point 2 could be said to present a highly compressed gaseous state of the substance. Whether we refer to the state in the region of point Z as liquid state or highly compressed gaseous state depends purely upon which of the two viewpoints happen to be convenient at the moment. Thus, in the absence of the surface of discontinuity, there is no way of distinguish between liquid and gas. So, van der Waals equation and critical state, Thomas in 1871 studied the isotherm of carbon dioxide drawn by Andrews. He suggested that there should be no sharp points in the isotherm below the critical temperature, and this isotherm should really exhibit a complete continuity of a state from gas to liquid, and this he showed by a theoretical wave curve. Look at this picture. We are talking about this curve, and then we are talking about this critical point, the curve this, and the maximum point of curve, this is the critical point. At temperature, this is critical temperature. For volume, critical volume. Pressure, critical pressure. So critical isotherm, and this is designations of A. You can see the B, you can see the D, C and D. You can see the N, M, and L. This is the pressure volume isotherm of carbon dioxide. The curve MLB, you can see MLB, this in this figure represents a gas compressed in a way that would remain stable. This curve. The curve M and C, this curve, represent a superheated liquid. This type of discontinuity of state is predicted by von der Waals cubic equations. According to it, for any given values of pressure and temperature, there should be three values of V and volume, and these values are indicated by BMC. Look at BMC, this value, and this value. BMC of the curve. The three values of volume becomes closer as the horizontal part of the isotherm. At the critical point, these values become identical. This enables the calculation of critical temperature, critical pressure, and critical volume in terms of van der Waals constants. So van der Waals equations may be written as P A by V square V minus B RT 4. So PV minus PB plus A by V minus AB divided by V square is equal to RT, or PVQ minus RT plus PV under bracket a small bracket V2 plus AB minus AB is equal to 0. At critical point, V is equal to Vc, critical volume. V minus Vc is equal to 0. V minus Vc cube is equal to 0. So, Vq minus 3V square Vc plus 3V Vc square minus Vc cube is equal to 0. Thus, at critical point, van der Waals equations gives Vq minus RTC divided by P plus B, V square plus A divided by PC, V minus AB divided by PC is equal to 0. So, equations coefficient in 1 and 2, 3Vc is equal to RTC divided by PC plus B, equation 4. 3Vc square is equal to A by PC, equation 4, and Vc cube is equal to AB divided by PC, equation 5. So from equation 4 and 5, Vc is equal to 3B. Substituting this value in equation 4, we get PC is equal to A by 27B square. Substituting the values of PC and Vc in equation 3, PC means critical pressure, TC means critical temperature, Vc means critical volume. So critical temperature becomes 8 by A divided by 27 RB. Knowing the value of A and B, the critical constant can easily calculate. Conversely, since PC, critical pressure, and TC, critical temperature, can often be determined experimentally with some case, and these values may be employed to calculate the constants A and B. So A is equal to 3Vc square PC and B is equal to Vc by 3. So the actual determination of critical constant is often a task of considerable difficulty. Of this critical pressure and critical temperature can be measured relatively easily with the help of Cagniard-de la Tour's apparatus, and the most accurate method for determination of critical volume in due. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.